Okay, so today we're going to have a look at Spearman's rank correlation coefficient. We sometimes just call it Spearman's rank or Spearman's correlation. It doesn't really matter. Right, so let's have a look. So we're going to have a look at the equation, how we use it and what we use it for, and what your data, what kind of data you must have for Spearman's rank. So we are going to have a look at association. So we've got a couple of examples here comparing the price of a cup of coffee with the distance from the Eiffel Tower, the height of year 12 girls compared to the length of their skirt. Always useful. So it's looking at the relationship between two variables. As one goes up, does the other go up? As one goes up, does the other go down? Or is there no relationship whatsoever? So there's no association at all. So we've got some graphs here, so you can see this one shows you a positive correlation. So as you go up on the x-axis, you also go up on the y-axis. A negative correlation, as you go up on the x-axis, you go down on the y-axis, and you can see this one over here, you've got no correlation. Now the difficulty is, if you're, these two here, this one and this one, are quite easy to see that there's a correlation. Those data points are quite clustered. They do form a reasonable line. The difficulty is, the further apart they get, the more difficult it is to decide if there is a relationship or not. And so that's why we have this statistical test. With all statistics, what it does is takes out your opinion. So you calculate something, you compare it to a critical value, and that tells you whether or not there is a relationship, whether or not you should accept or reject your null hypothesis. So again, with this, the null hypothesis is always that there is no relationship. If you accept the null hypothesis, you're saying, yep, these two things aren't related. You've got a graph that looks possibly a little bit more like this one. If you reject the null hypothesis, you're saying actually there is a relationship. As one goes up, the other one does go up, or if one goes up, the other one does go down. So that's what we're going to have a look at. And so again, we're going to be using critical values. Again, in the exam, you will be given the formulas and you will be given at least one critical value, if not more than one. For this, you're usually just given the one critical value to use. Right, so I just said all of this already. So when the points don't neatly fit on that line, it's not up to you to make a judgment. That's not what we're here for. We collect the data and then we use maths to decide what we should do with that answer, what the conclusion is. So as I said, we look for association between two variables. Now you need quantitative data for both variables. You need to be able to put them in size order. If you cannot put both your independent and your dependent variable, if you can't put those in size order, 1, 2, 3, 4, 5, 5.5, 6.7, 9.2, whatever it is, if you can't put them in order, you can't use Spearman's rank. Okay? Right, so this is the equation. Now it looks horrendous, but we have seen elements of this before. So we've had a look at this before. So this means you add up whatever comes next. We've seen this before. This is the difference. Now this isn't the difference in the values. This isn't the difference between your value for your independent variable and the value for your dependent variable. This is the difference in the rank that you are going to assign to it. And we'll have a look at that in an example. It's a lot easier to see it in an example. So you need to find out the difference between your rankings. You need to square them, and then you need to add them all up. And then when you have that value, when you have that one value, you times it by 6, and then you're dividing by things we've seen before. So that's just the number of data points that you've got. That is the number of data points squared minus 1. And so this can also be written as n cubed minus n. It's exactly the same as n brackets n squared minus 1 it's exactly the same as n cubed minus n. So the one thing most people forget to do is take all of this away from 1. It's the final step, and lots of people lose marks because that's the bit they forget to do. Okay, so we're going to have a look at this example. Do whales get heavier as they get longer? So as you increase the length, do you also increase the mass? Now, as good scientists, usually your independent variable is already in size order. So you can see here, these are already in size order, but do not count on it. Look at the data. These ones are definitely not in size order. You can't have both of them in size order to begin with, can you? So, does it look like as you increase the length, you also increase the mass? Well, yes, it does look like that from the graph, from the table, but do you know that for certain? So that's what Spearman's rank is for, okay? So the first thing we need to do is actually assign a rank to them. So if you drew this graph, you would probably get an uphill line, but how close to an uphill line? Is it, is it a good enough, a tight enough uphill line? So we are working with a null hypothesis always, so there is no correlation between the variables, and you have to mention both variables in your null hypothesis. So there is no correlation between the length of the blue whale and the mass of the whale. Okay? Right, so you need to rank them. So for each set of data, you rank them lowest to highest. So the smallest number gets a ranking of 1, the highest number, the biggest number, gets a ranking of however many data points you've got. If you've got 20 data points, then the largest number is going to have a ranking of 20. Now, the difficulty is if you have 2 values that are the same, then you work out the mean. If you have 3 values that are the same, you work out the mean and you give all of those the same mean. Now that can be quite a difficult concept, so let's just have a quick look at an example. So you can see here we've got the length of the whales as we had before, and we've got the mass of the whales, and this is what we mean by ranking them. You assign them a number in order. Now, because this was a well-constructed table, these ones are already in size order, but you can see there are 2 of them that are the same. So we work out, so they would have been 8 and 9, but because they are the same value, we give them the same rank. So you don't work out the mean of the 2 values, you work out the mean of the rank. So a ranking of 8 and 9 would give you a mean of 8.5. So they both get 8.5, but then look, you then jump to the next one. So if they would have been 8 and 9, for example, that didn't work. That's terrible. So if they would have been 8 and 9, they both get 8.5, and then the next rank jumps up to 10. Okay, so you can see there, jumps up to 10. So it goes 1, 2, 3, 4, 5, 6, 7, 8.5, 8.5, 10, 11, 12. And if you had 3 that were the same, you'd give them the same mean and then jump up to 11. Okay? Right, now you can see over here, you do have to actually rank them. You have to find which one is the lowest, find which one is the second lowest, etc. So you can see 1.5 is the lowest, 2.3 is next, and then it jumps up here. 2.6 is the 3rd highest, and then 3.6 is the 4th highest. 7.1 is the 5th highest, etc. Okay, so you assign them this ranking. Okay, now when we work out the differences, we're working out the differences of this set of numbers to this set of numbers. We are ignoring the data from now on. We're just going to look at the ranks. Okay, that's what we're going to work out the difference of. So you can see here, you've got a rank of 1, a rank of 1, so the difference is 0, and then when you square it, surprise, surprise, you get 0. Now if you get minus numbers, like here, 3 minus 4 is minus 1, don't worry about the minuses, because the second you square it, you get rid of the minuses anyway. So if we have a look at this one, you've got a ranking of 6, a ranking of 11. When you work out the difference, you've got minus 5, and so when you square that, you've got 25, for example. Here you've got a rank of 10, a rank of 7, your difference is 3, 3 squared is 9. Okay, so you work out the difference between all of these ranks, you square these numbers, so you just take these numbers and square them, and then the bit that we want is this. This is the sum of d squared. Okay, so that bit of the equation we've already worked out. So you work out the difference, you square it for each number, and then you add all of those d squares together, and that will give you the sum of d squared. Okay, so we've got that bit, and we know we had 12 whales, so we know what n is, and so we can work out all of that. So it is 1 minus 6 times 47.5 was our d squared, divided by 12, because that's what n was, brackets 12 squared minus 1. So that's the whole equation. And don't forget 1 minus all of this. Okay, so plugging that in, if you have a look at the different bits, we've already got that bit, and so we can plug it into the equation, and so you would have your RS value, choose a different colour, equals 1 minus, and you've got 6 times 47.5 over 12 squared minus 1. What they've done here is they've just taken out these brackets, so that would be 12 cubed minus 12. It's exactly the same thing. Okay, so you work out all of that, and it's take that away from 1. And again, write this in your exam. Write out all of this in your exam. That is showing you're working. They want to see you can put the numbers into the equation. So once you've done that, you just plug all of this into your calculator, and you should get 0.834. So 0.834, is that a strong enough correlation? Again, not your job to decide. The mathematicians have come up with these critical values, so we compare this value to your critical value. So let's have a look. So now the problem is with correlation, you can have a positive correlation and you can have a negative correlation. Now your RS value can work out to be a negative number. Okay, it can be a negative number, it can be a positive number, because if you have a look up here, a perfect negative correlation will be -1, a perfect positive correlation will be +1, and the closer it is to 0, the closer it is to having no correlation. Now the critical values only ever come as positive numbers. So if your RS value works out to be a negative number, you just put a minus in front of your critical value. It doesn't matter that the critical value given to you is positive. If your RS value is negative, you simply put a negative in front of your critical value. Okay, so we want to have a look. How close is our value to 0? How close is it to either -1 or +1? Now we had 0.8 something, so ours is a positive correlation. So we want to know how close it is to 1. So the closer it is to 1, the more positive the correlation. The closer it is to 0, the less likely there is to be a correlation. So let's have a look. So we've got our critical values, and that's what we're going to use to decide whether we should be accepting or rejecting our null hypothesis. So we had 12 values, and you'll see in your book there's some critical value tables. So for 12 values, we get a critical value of 0.59. Now we make it positive because we had a positive Spearman's rank number. If we had had a negative Spearman's rank, we would have just put a minus in front of our critical value. Okay, so Spearman's rank is 0.34. Our value is bigger. It is a larger number than the critical value. The critical value is 0.59. 0.834 is a bigger number. Now, this is where it gets tricky, because if we have 0 here and we have -1 there and we have +1 there, if that was minus, it would be all the way down here somewhere. And sometimes it is very tempting to say our RS value is greater than our critical value. If our critical value was here, for example, and it wouldn't be. Minus 0.83 is not bigger than minus 0.59. So be very, very careful with your wording. So the wording I prefer is that it is closer to -1 or closer to +1. Our RS value is closer to +1, or our RS value is closer to -1 than the critical value, and so we will reject the null hypothesis. So be very careful if you say greater than, because minus 0.834 is not greater than minus 0.59. It is a more negative number. So you can use phrases like more negative, less negative. You can use phrasing like closer to -1, closer to 0. Okay, so what I would do in an exam, because I just can't visualize numbers in the same way that other people would, I would put 0. I would put, to be perfectly honest, I would probably put +1 over there and -1 down here. I would write in where my critical value is. I would write in where my value is, so the exam board can see I do know what I'm talking about. I may not have phrased it in the best way. And I would say our RS value is closer to +1 than the critical value, and so we will reject the null hypothesis. And the null hypothesis is that there is no correlation. So the closer it is to 0, the more likely it is that there is no correlation. So that's when you would be accepting your null hypothesis. So anywhere between your critical value and 0 is where you will be accepting your null hypothesis. Anything between your critical value and 1, you will be rejecting your null hypothesis. I'm very sorry that I've just scribbled that all over the writing. Okay, so our RS value between 0 and the critical value, you accept the null hypothesis, there is no correlation. RS between the critical value and either +1 or -1, you reject the null hypothesis, there is no correlation. So if I just do 0 and +1 up here, if that is your RS value and that is your critical value, that was a line, your value is here, it's closer to 1. If your value was along here somewhere, you would be accepting your null hypothesis, closer to 0, closer to there being no correlation. But your value is up here, so it's closer to having a proper correlation. Okay, so that's what I mean about drawing it out, because it's a lot easier. If it was a negative number, then if that was your critical value and that was your RS value, you would still be rejecting the null hypothesis because your value is closer to -1. It's closer to an actual correlation. If your value was here, it's closer to 0. So you would be accepting your null hypothesis there. Okay, does that make sense? So let's just get rid of all of this so you can actually read the PowerPoint. So it says here, our calculated value of Spearman's rank is plus 0.834. It is larger than the critical value of 0.59. And this is what I would use. It is nearer to +1. So we reject our null hypothesis. Okay, so I would say at p equals 0.05 or whatever critical value you'd be given, we're confident that as wear length increases, so does mass. Okay, this bit, if you're a maths person, you can use this. If you're not a maths person, I wouldn't worry about that wording. But again, remember to always include your Spearman's number, your critical value, what p-value you're using, and then is there or is there not a correlation? Are you accepting or rejecting your null hypothesis? Remember, you've always got to include your value, the critical value, the p, what probability level you're using, accepting or rejecting your null hypothesis, and relate that to the question. We accept our null hypothesis, there is no difference. We reject our null hypothesis, there is a difference. Okay? Right, so once you've had a look at the worked examples, you can go through the rest of the questions and you can see here how to word your conclusions. Okay, get used to this wording. And they've included all of the elements that you need. Okay, so work through these examples in your own time, pausing and kind of moving on as you need to. Okay.